Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 21st, 2025, about 4 days ago. It shows that a full stack built entirely on AMD hardware, from MI300X graphics processors to the Pollara high-speed network and the ROCm software stack, can reliably train mixture of experts' foundation models that match or beat well-known NVIDIA-based models on reasoning, math, and coding benchmarks. The paper is titled, Training Foundation Models on a Full-Stack AMD Platform, Compute, Networking, and System Design. And, as we will see later, the combination of careful system measurements and model design leads to some surprisingly competitive, large-scale training results. Alright, Figure 1 lays out the full AMD software stack that supports ZAYA1 training. The bottom block shows the high-performance computing hardware, with MI300X accelerators, standard CPU compute, fast NVMe and parallel file storage, and PCI Express Pollara and Infinity Fabric interconnects. Above that, compute kernels in HIP, Triton, and composable kernel provide optimized attention, transformer, and matrix multiplication routines, while communication libraries handle distributed messaging. At the top, PyTorch and Megatron LM and Python deliver the deep learning frameworks that researchers actually script against. Well, after Figure 1 focused on the software stack, Figure 2 turns to the physical cluster that actually runs ZAYA1 training. The left panel shows a single node with 8 MI300X graphics processors tightly interconnected, each paired with its own Pollara network card and local NVMe storage, so compute and I/O stay balanced. The right panel shows how dozens of these nodes link into a two-level rails-only network, where leaf and spine switches form parallel rails that spread traffic and reduce congestion during large-scale training. So while Figure 2 described how nodes connect, Table I spells out what actually sits inside each box. The compute nodes carry 8 MI300X graphics processors, 2 terabytes of DDR5 memory, dual Intel Xeon Platinum processors, 8 Pollara 400 gigabit per second network cards, and about 26 terabytes of NVMe storage. The storage nodes trade graphics processors for 120 terabytes of NVMe in a high throughput array. The login nodes are comparatively lightweight, with modest memory and CPU, since they only handle orchestration and user access. So after Table I detailed the node components, Figure 3 shows how fast the high bandwidth memory actually moves data during PyTorch workloads. The curve plots bandwidth versus buffer size, and it reveals that both graphics processors only reach full speed once transfers reach about 16 megabytes. The MI300X line then flattens around 4.3 terabytes per second, while the H100 tops out near 3 terabytes per second, which means the AMD chip delivers roughly 40% more sustained memory bandwidth. Alright, while Figure 3 highlighted memory bandwidth, Figure 8 dives into the ZAYA1 model architecture. The central block shows a transformer layer repeated many times, where self-attention feeds into a mixture of 16 experts controlled by a router. The left inset details the router, which first normalizes and compresses the token, applies an exponential depth averaging step, then passes it through 3 small multi-layer perceptrons. The right inset illustrates compressed convolutional attention, which reshapes queries, keys, and values with depth-wise and head-wise convolutions, plus a time delay to cut computation and memory while preserving context modeling. So, while Figure 8 dug into the architecture, Table IV shows how that design translates into benchmark scores. ZAYA1 base reaches about 67% accuracy on standard MMLU, and around 40% on MMLU Pro, which matches or trails QN34 billion only slightly despite far fewer active parameters. The model strongly beats the older MoE mixture of experts, especially on hard math and coding. Compared with dense 7 to 12 billion parameter models, it remains broadly competitive, which makes the efficiency of the mixture of experts design very clear. So the big message is that a carefully tuned AMD stack, from MI300X hardware to ROCm software, can pre-train mixture of experts models that are genuinely competitive with leading dense models, not just as a low-cost backup. The broader implication is real vendor diversity for large model training. That is it for this episode of the AI Research Roundup. I am Alex, thanks for listening.